Alright, here we go. Ooh, I'm starting with a yawn. That's a bad sign, but that's okay. We're going to turn it around. So here's what we're going to do. We are going to fill in these questions. We're going to explain them. You're going to get it, and it's going to be great. So we're on the photoelectric effect. Hopefully you're on that one. Atomic spectra. Alright, so let's look at number one. A blank is just energy carried from one place to another, sometimes through a medium. So, you guys probably already know this one. Hopefully you do by now, since you're on most likely the last unit of physics. But this one is a wave. So we are talking about light. We know light travels in waves. Electromagnetic radiation travels in waves. And sound travels in a different kind of waves, but also waves, really. It's kind of like vibrations, compression waves. But, so, sometimes through a medium. What this means, just as an FYI, this just means like, medium means like middle. So like, me talking, my voice goes, sound from my voice goes from me to the microphone, but it travels, the median in this case is air. If I knock on this table, the median is whatever this table is made out of, plastic, right? So on and so forth. It could be underwater, and the medium would be water, all right? So, draw and label a wave. Okay, you guys probably know how to do this by now also, but let's do it anyway. So, you already know what a wave looks like, right? So that's probably the easy part. The harder part, or the part that, is a little bit more challenging, is the labeling. So here's our wave. This will be our electromagnetic wave. Let's label everything there's labeled. So first off, the amplitude. Some people mistakenly say the amplitude is from top to bottom, but it's actually not. The amplitude is from midline to top, or midline to bottom. So I'll put it over here so you know it's not top to bottom. So this right here would be the amplitude. Okay? You know that the top is the crest. You probably could have figured that out. The bottom is the trough. That just means the bottom. And the wavelength is just from, so for example, crest to crest. So from here, in this case, to here would be the wavelength. Alright, so there is our wave. We've drawn it, we've labeled it, it's completely done. So again, the only things to note that I would be concerned that you might not remember is amplitude is from center line to top or bottom, but not both, right? And wavelength is from like crest to crest. You could move the whole thing over and say trough to trough. It would be the same thing, but just note it's from one point to the same point on the next wave. So you wouldn't put it here to here, right? It's complete wavelength. Okay, let's look at number 3. How are frequency and wavelength related? Let's look at two waves. Here's my one wave, and here's my other wave. Okay? Notice one of them has a very high frequency. One of them has a very high wavelength. You could probably guess, because now that you know what wavelength is, that the one on the right has a pretty big wavelength as compared to the one on the left. But the one on the left has a higher frequency. Frequency is just how often it goes up and down. That's kind of like the brief definition. How often it goes up and down, we'll say in a given time, right? So it looks like they are inversely related. So what that means is that as one increases, the other decreases. So it's like an opposite relationship. So as one increases, the other decreases. As one decreases, the other increases. And that makes sense, right? If I expanded my wavelength out, the frequency would naturally be less because it wouldn't be going up and down as often, right? And vice versa. If I brought my wavelength in, the frequency would increase a lot, right? Okay, so let's look at this. Now that we know that it is an inverse relationship, meaning like opposite relationship, if the frequency doubles, what happens to the wavelength? So think about this. If I let's say our frequency, we'll call it F. Right? Is that the formula? Yeah. If my frequency is 2, doubled, 2F just means doubled, right? What happens to the wavelength? Well, since it's an opposite relationship, and the wavelength's drawn, how do you draw that wavelength? It's like this, weird. it wouldn't be 2 on the top. Inverse means opposite, so we'd put a 2 on the bottom. So what does that mean? It means divided by 2, right? Hopefully that made sense. That was kind of a long explanation. Hopefully it wasn't confusing. But the point being that whatever you do to one, you do the opposite to the other. So if you double the frequency, you divide the wavelength by 2, and vice versa, right? Okay, how big or small can waves be? So remember, oh man, let me pause it and look up a picture. Okay, so I've Googled, I've searched up wavelength sizes. This is just a general picture. It could be a different picture, but it's whatever. So notice that wavelengths can be, waves can be as small as like atoms' nuclei, like super, super small. That's smaller than atoms, right? Or they can be as big as buildings. Okay, so that's something to consider. They can be huge. So you see the one on the far left, larger radio waves, really, really big, right? Versus super, super tiny gamma rays. Keeping in mind that the bigger the wavelength, the less energy. So these huge waves on the left, they're not very high energy, right? Whereas these gamma rays on the right, very, very high energy. Okay, so that's that, right? So however you want to word this, I'm going to go ahead and say as large as a building or as small as an atom. Or you could say atomic nuclei, really. That was a better deal. All right, number 6. We can use the blank to help determine one element from another. Awesome. Yeah, so that's electromagnetic spectrum. And I'm going to explain that in just a second. So let's go back to our search bar. Let's check this out. So let's go, done with this. Let's scroll up here and let's put spectral lines. Awesome. So it doesn't really matter. Let's click this one. Let's check it out. Okay, so observe. Really weird looking thing going on here, right? You have a black bar. You have certain lines, and then it tells you kind of like the length of those lines, the nanometers of the lines, and then the elements. So spectral lines like this are sort of like the element's fingerprint, right? It's unique to that element. So the top element was hydrogen. Only hydrogen has spectral lines like that. So, you can look at certain like stars. A lot of times use a spectrometer, and you'll see certain lines if that star has hydrogen. Now, pretty much all stars have hydrogen. Now, the amount's going to change, but the bottom line is you can see what star has what elements and light and things like that. When you're burning certain elements, or when you have a tube and you have, like, let's say we have helium in it and we run electricity through it, it'll give off certain spectral lines. You got to look through a spectroscope, but that's the point. So we can use electromagnetic spectrum to determine one element from another. Awesome. Let us keep going. What are some of the things we get from emission spectra? So from looking at these spectra, light bulbs would be something. And more specifically about light bulbs, for instance, neon signs. It's a neon sign because it has a certain glass in that tube, a certain gas in that tube, and you run electricity through it, and that gas emits a specific color, right? And different gases emit different colors. Okay, glow sticks is another example. Glow sticks and fireworks. Fireworks is a great example. You have different materials, given energy, and they emit specific colors. All right, list all the colors of visible light from shortest to longest wavelength. Okay, let's go back to search. Let's search this up so we can see it. So there we go. Awesome. This is the picture that I wanted. So here we go. Visible light. Dang, we're not loading. That ain't no good. Gotta load, my friend. You gotta load. Let's just click it straight up. Okay, Wikipedia. I'll take it. You could have done that first. That was a waste of my time, but that's okay. So, we have visible light here, right? So observe the picture. Now the question is, list all visible light. Let's crank this up a little bit. List all the colors of the visible light from shortest to longest. So really you know the colors. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, right? So the question is shortest to longest. So if we check that out, we can see that the shortest is closer to the right, right? And the longest is they're talking about wavelength, is closer to the left. So in that case, naturally, you know, the way most people memorize it is Roy G. Biv. Hopefully you guys have heard that. Red, orange, yellow, green, blue, indigo, violet. Well, shortest wavelength would start with violet, right? So you would go violet, indigo. I don't know how to spell that, so we're just going to go with it. Blue. Indigo is like a purple, right? Green. Yellow. You guys can probably finish this, but I'm doing it anyways. Orange. And red. So, in terms of energy, red would have the least amount of energy, and then violet would have the most amount of energy. Which is like when you get into that ultraviolet, that's a bit higher energy, like UV rays, right? So there you go. So remember, we are going shortest to longest. So the shortest wavelength is violet. So we're talking like pretty short. The longest wavelength is red. Not drawn to scale. Number 9. What equation do we use to calculate the speed of light? You guys can Google this if you want, or you can wait till I finish this sentence and write it down. So the speed of light, as an FYI, is c in physics, and that is our frequency times our wavelength. So this is our wavelength, this symbol thing here, and this is our frequency, right? Pretty simple. In this equation, what does c stand for? C stands for the speed of light. Speed of light. Now here's a big question that you probably didn't ask, but initially when I saw this I was thinking, wait a minute, the speed of light is always constant, right? If we average it off, it's like 300,000 meters per second, something like that. Let's look it up. We're mid-video, we can do it. We'll do it live. Speed of light. I'll write it and we'll do it live. Okay, cool, so we were right. We rounded that up, 299,000, actually no. That's faster than that. That's faster than that. Let's scroll over. Let's see. Miles per hour at 671 million miles per hour. Okay. 1,299,792,458 meters per second. That's pretty fast, right? So the deal is, speed of light is supposed to be a constant. So then why am I looking at this formula and it's like, well, you calculate it by wavelength times frequency. Well, keep in mind what we learned earlier. So it should be constant. That number is consistent. Keep in mind what we learned earlier, which is that they are inversely related. So if I have a small wavelength, so this is very small, then our frequency is high, right? So if this is small, this has got to be high. So then again, it balances this out. And likewise, if I have a large wavelength, then this is big and the frequency is small. And again, this number is still consistent, right? So there's a formula for it. but this C is always the same. Alright, true or false? Electromagnetic waves travel at different speeds. Well, we just sort of answered that, didn't we? Maybe this is radio, and maybe this is UV. Two different waves, two different frequencies. Use our pointing device. High frequency, low frequency. Large wavelength, small wavelength. Same speed, right? Same exact speed. So in this case, we're looking at false, right? Same speed. They might have different wavelengths, different frequencies. Alas, though, the speed is the same. All right, let's keep going. Number 12, and we're at about 16 minutes. So if you got to pause, that's when you know you restart. What is the frequency of green light, which has a wavelength of blah? Cool. So remember, what's our formula? Speed of light equals our wavelength times our frequency. This is always the same. What we're going to do is we're going to round this C, the speed of light, to 3.0 times 10 to the 8th. That's meters per second, right? Let's box it. Don't box it on here because then it's going to look like the answer. I just kind of box it because I wrote too close, right? So now we only need this and this. Well, in this case, we have wavelength, right? So we have 3.0 times 10 to the 8, sorry, not minus 8, equals, we have wavelength, so 4.9 times 10 to the minus 7, pretty small wavelength, times frequency. Well, that's easy. I mean, this is the same Algebra 1 stuff you've already done. You got to divide this out. 4.9 times 10 to the minus 7. Cancel. 4.9 times 10 to the minus 7. And then, which means our frequency is, hopefully you guys calculated this, about 6.1 times 10 to the 14, and then frequency is in hertz, just as an FYI, right? Cool. I mean, this stuff is going to be super easy. Again, this is like your basic Algebra 1. It's basically like 10 equals 2x. I mean, that's all you're doing. Divide the 2 out, x equals 5, right? Easy. I mean, this is pretty easy stuff. X-ray has a wavelength of 1.15 times 10 to the minus 10. What is its frequency? Again, I'm going to write my speed of light because I have that, times 10 to the 8th. I'm going to write my wavelength, weirdo sign, equals 1.15 times 10 to the minus 10. Frequency I don't know. Then I'm going to write it out. 3.0 times 10 to the 8 equals 1.15 times 10 to the minus 10 times frequency. Divide it out. Easy. It's Algebra 1. That's all it is. Algebra 1. This is middle school algebra, actually. It just keeps getting easier. 10 to the 18. Frequencies in hertz. There you go. Easy. What is the speed of electromagnetic wave that has a frequency of that? Okay, so now they're finally changing it up, right? So again, speed of light equals 3.0 times 10 to the 8th. Sorry, what am I doing? I'm losing my mind. 3.0 times 10 to the 8th. That's the speed of light. Frequency equals 7.8 times 10 to the 6. That's in hertz. Easy. Wavelength equals we don't know, right? So we have our speed of light, 3.0 times 10 to the 8 equals our wavelength, have fun drawing this every time, times our frequency, 7.8 times 10 to the 6. Same thing. Divide it out. Cancel. Divide it out. And then that means our frequency is, you should get about 3.0 times 10 to the 8th. Remember, frequency is Oh, my bad. I'm sorry. Did I do this wrong? I did it wrong. What is the speed of an electromagnetic wave that has a frequency of that? We didn't need to do all that. I did this completely wrong. Hopefully you caught that. That's good. That was a test. This was all a test. I wanted to see if you were with me. So we didn't need to do any of this. I just went to autopilot and did it wrong. It wasn't this. I was thinking it was. Really, we're finding C. You automatically know C. You all passed the test. Congratulations. That was completely a test. I knew exactly what I'm doing. All right, number 15. A popular radio station broadcasts with a frequency of blah. What is the wavelength? Okay. This is not a test. We're live. We are live. Speed of light equals 3.0 times 10 to the 8th. Our frequency equals 94.7. Notice they give it to us in megahertz, and they actually convert this one for us, so that's great. So they convert it to hertz for us, so it's 94.7 times 10 to the 8th hertz. If you want to say 9.47 times 10 to the 7, that's fine too. Hopefully that made sense. And then we need wavelength. So again, speed of light, 3.0 times 10 to the 8th equals, we don't have our wavelength, but we have our frequency. I'm going to change it. I'm going to say 9.47 times 10 to the 7. Hopefully that's good. Again, divide it out. 9.47 times 10 to the 7, gone. 9.47 times 10 to the 7. So, our wavelength equals 0.032 meters. And then depending on what you do, you might also get 0.0317. So depending on if you convert this or not, whatever. So if you get one of these, you're good to go, okay? All right, so number 16. What is the electromagnetic spectrum? Feel free to Google this. Feel free to look in your physics books. Feel free to look wherever you want. Just keep in mind, you know, sometimes if you do Google something, just look at a few different definitions. Sometimes that helps you sort of like triangulate the proper definition, right? So, 16. The naming of a specific type of radiation energy ranging from short gamma rays to long radio waves. That's all it is. It's just a way for, you know, we name stuff. We're humans. We name things and we classify things. That's the way we're programmed. Imagine you come to Earth. You've never been here before. The first thing you start doing, we figure stuff out. We label things. So that way we know, we can identify and interact. This is the same thing. It's just a more sciencey version of that. We know everything else. Let's start labeling like the stuff we don't see, like waves. So I'm not going to write that out. But again, the naming of specific types of radiation ranging from short gamma rays, short wavelength gamma rays, to long radio waves. So there you go. That one's done. Easy. We did it. It only took us, what, 23 and a half minutes. Okay, never mind. We're not done. But we're almost there. We're almost there. Can we beat 30 minutes? This is a long time. It's taking a long time. We can do it. It's taking so long. It's okay. All right. Fill in the missing word below. So, ground state. The base or low energy state of a blank. So, hopefully you remember this from like middle school where you're doing electron shells, where you have your small center, and then it's like 2 can fit on this one, and then it's like 8, and it goes on and on. I think it's 288, but whatevs. So the ground state is the lowest energy state, or the normal like state of an electron. All right, cool. The next one, the process of taking in energy. So I'm going to start by just saying it's absorption. Did I spell that right? Absorption? Yeah, good. So actually absorption. Oops. That's cool. All right. So remember, think about a complex fluorescent light, or probably you can most likely look up in the classroom and notice those tubes they just have the long tube lights, and usually classrooms and buildings, they just have gas in them. You turn on the switch, electricity goes through from one end to the other end. That gas absorbs that electricity. Once it absorbs it, those electrons jump to outer shells, right? They absorb that light, or they absorb that energy. They jump to outer shells. When they fall back down, they release photons, right? So that's all that is. Absorption releases photons, right? Okay, emit or emission, giving something. Okay, it's common. So this would be like giving something off, or like releasing. And just like we said, you have that atom. It absorbs energy, right? Those electrons jump to outer shells. When they come back down, it releases that energy in the form of like a photon, right? All right, the next thing, quanta. Okay, quanta is a tiny unit of energy released by an atom, right? So this is just simple. We're just going to say a tiny unit. It's released by an atom, like a photon. Too much quiet. I thought these were connected. My bad. Released by an atom. So this one is a photon. So this would be what gets released when that when that gas or element absorbs that energy. It releases a photon, a particle of light. So it's a specific type of tiny unit, right? All right. So spectra, the unique lines produced from, and remember we talked about this, everything has its own fingerprint. So this is element. So every element, like earlier in this video where we saw those lines, you had this long thing, and then like depending on what element, it'd have like a line here, two here, maybe this one's thick and one here. It's always unique to that element, right? So as they emit, again, this is photons. All right, photoluminescence. So you know photo means light, right? The process of giving off light as electrons fall. So as they kind of like fall, or really they go back to their normal state, right? They go back to their ground state, really. So what happens to an electron? What happens when an electron returns to ground state? Well, we said this earlier. When it returns to its ground state, let's redraw this picture because I'm an amazing drawer, so I'm going to draw it. So we have a normal electron here, E. Gets energy, boom, jumps to this shell, E. Comes back down, releases photon. Photon cannon. So it just emits a photon. Cool. All right, so 19. What happens when an electron absorbs energy? Well, when it absorbs energy, it jumps to a higher shell, right? So jumps to higher, you could say shell, you could say energy level. I like shell better, even though I wrote energy level. Whatevs. So, who discovered that objects can absorb or emit only certain amounts of energy? So that would be this, my boy Max Planck. P-L-A-N-C-K. My homeboy. Alright, 21. Different blank equals different amounts of energy. So, different colors means different amounts of energy. Awesome. Number 23. Each element emits different blank when you heat it. Did I skip one? I think I skipped one. Oh, I did 23. Oops. Let's go 22. Photons with higher blank have more energy. Remember, our answer choices are wavelength or frequency, right? So, photons with higher frequency have more energy. Awesome. Now we're to 23. Each element emits different blank when you heat it. So each element emits different. So back up here, you could say spectral lines, but let's just keep it simple. Let's say colors. Each element emits different colors when you heat it. Keep in mind, heat it sort of means like give it energy, because if you heat something up, you're giving it energy. So just keep that in mind. Heat and energy are similar, one and the same. Alright, you can identify elements by their blank, like atomic fingerprints. We went over this. Ooh, let's bring this up. So remember, with this emission spectrum, emission spectra. Do we make good time? Do we make it? Oh, it's over 30 minutes. You lose. KO. Alright, no worries. But that's like a minute and a half a problem, something like that. You guys will have to do the math. Man, I'm so bad at algebra. I couldn't do it. You guys can do it. Whatever. Alright, cool. So that's done. We did the first page. If you guys got questions, let me know. Great job. And cancel.